All right, I want to calculate the magnetic field due to a wire carrying current I. This is a straight wire. And when we calculate the magnetic field at a point D above it, and its location is 0, comma D. Here's the origin of my system. And the first thing I want to do is write the expression for ds, which is my element of carrying current I. So my ds, since the current is going in the positive x direction, and this little piece of the entire wire is of length dx, I'm going to write down ds is I dx. Okay. My next step is to derive an expression for r hat. R hat, again, is the vector that goes from the source here to the point P. So let me draw that in. And I'm going to write it in terms of the angle theta. Well, the unit vector has a component this way and a component this way. The horizontal component is cosine theta, I hat. The vertical component is sine of theta, j hat. Then my r squared term. I can write it different ways. If ds is a distance x from the origin, then the magnitude of this vector is going to be x squared plus d squared, just x squared plus d squared. The next thing is to calculate ds cross r hat, which is this cross with this. When I take the cross product of this guy with this guy, the I component will cancel because I cross I is 0. I cross j is in the k direction. And so this is going to be that. And if you don't see that right away, you can always set up the determinant to calculate the cross product. The next step then is to write the expression for dB. Using Biot Savart law. And then here I put ds cross r, which is now it's kind of weird because I have some x's there and a trigonometric function, so I'm going to have to change that to make the problem a little bit easier to work with, at least in terms of me having to do the integration. We should think about which direction the field really is at point P. If I use the right-hand rule, I put my thumb in the direction of the current. My fingers curl like so. So the field at the top comes out of the board. The field below goes into the board. So at point P, it's in a positive k direction, which makes sense with this. Now to make this, to allow me to do the integral, I'm going to replace my x in terms of trigonometric functions. I'm going to define, because x here is d cotangent of theta, I'm going to say x is equal to minus d cotangent of theta. Why is there a minus sign there? Because on this side of the axis, x is negative, although cotangent of theta will be positive. So I got to make sure that x is negative. Okay. Then dx is d cosecant squared theta d theta. Now what is this going to be? X squared plus d squared is d squared cotangent squared theta plus d squared. I factor out d squared. Now you have to remember your trigonometric identities. This ends up being cosecant squared. Okay, so this is cosecant squared. This has a cosecant squared. So the cosecant squared will cancel. Okay, so let's put this together just so we see this. And I'm going to leave the sine of theta for now. So dx is this guy. And then in the denominator, I'm going to put this. These two guys will cancel. And then this will cancel with one of these. And so I'm going to get u naught I over 4 pi times the sine of theta, d theta, over d. Now I can integrate. I'm going to integrate from theta 1 to theta 2. Of course, the integral of sine of theta is minus the cosine of theta. So I'll get the following. And one thing I forgot here is my unit vector k hat. Okay, oops. And I forgot that's b, sorry. All right, so now we have b is equal to that expression. And really that's it, but what I'm interested in is the case where the wire is infinitely long. Right? If the wire is infinitely long, then we have to determine what theta 1 and theta 2 are. So if the wire is infinitely long, theta 1 is 0, and theta 2 is pi. Okay. So if the wire is infinitely long, so if I put those values in here, I put cosine of pi here, I get 1. Cosine of 0 gives me 1. And so my field then ends up being And the term in parentheses represents the magnitude of the magnetic field due to an infinitely long wire, a distance d from the wire.